We've talked about the electric field that's caused by a producer, whether it be a positive producer or a negative producer. It doesn't really matter. We could find the value of that electric field by using the equation KQ over R squared. We've also talked about the electric field that's experienced by something. So you got a charge over here that experiences that electric field. We can find the value of that electric field by using the experiencer equation, E is equal to F over Q. Both of those are valid in the same situations. It's just a matter of what we have more information about. Do we have more information about the blue thing that caused the field or the green thing that experienced the field? Well, we're going to shift gears, but stay in the same car here. We're going to talk about electric fields here now again, but electric fields in a different context. This time we're going to talk about what we call a uniform electric field. This is a non-uniform electric field. It's not a constant field. We talked about this the day that we introduced this. The density of the field lines, how close the field lines are together, indicate the strength of the field. The field lines get further apart as they get further and further away from the producer. That means the field strength weakens. It's a non-uniform electric field. If we take a look at two parallel plates that are charged, one's positive, one's negative, then we'll find that the electric field strength is a uniform field. The field doesn't get stronger or weaker. It stays the same anywhere in between those plates. That's the field that we're going to talk about today. It's still an electric field. It's still newtons per coulomb. It still has the same effect. It's just that this time it's a uniform field as a non-uniform field. Now, that electric field that we're going to talk about today still could have the experiencer in between it. So we introduced an experiencer there, whether it be a positive field, sorry, a positive experiencer or a negative experiencer. It doesn't matter. The equation that describes the experiencer will still be F over Q. That doesn't change. The electric field experienced by an electron or a proton or an alpha particle in whatever field, uniform or non-uniform, is going to be F over Q. But the equation that we used to describe the non-uniform field, the one that we've used up until right now, isn't valid in this new situation because it's only valid for the non-uniform field. It's only valid for the point source. So we're not throwing it out. We're not saying that this equation can never be used again. In the situations for which you've already used it, it's still valid. But now in this new situation where we have a uniform field, we can't use it. Well, we better come up with something that we can use in that field then. We've still got the green equation, the one that describes the electric field experienced by something. But we need a new blue equation. The blue equation on the left-hand side describes the electric field caused by this point source. We need an equation that describes the electric field caused by these parallel plates. That equation looks like this. Delta V over delta D. Now take note of this equation, the delta V part of it. Delta V is a capital V. It's not a lowercase, so it's not a change in speed or a change in velocity. It has nothing to do with speed or velocity. It's a whole new variable that you haven't seen before. I'll tell you what it is in just a moment. Delta D, lowercase d. So now we've got two equations that apply in both situations. We've got what we call the producer equation that applies when we have a point source producer like we've had up until now. And we have an experiencer equation when an experiencer is in that non-uniform field. We also have a new producer equation, but a producer equation that's valid for the parallel plates or the uniform field, delta V over delta D, although you don't know how to use that yet. But we also have the same experiencer equation that we had before. That green equation, that experiencer equation, I sometimes call the universal electric field equation because it's always valid. Doesn't matter what kind of field we have, uniform or non-uniform, I'm allowed to use the green one. The blue one's the tricky one, because the blue one's the one that we have to decide, all right, what kind of producer do we have? One that makes a uniform field or one that makes a non-uniform field, and then decide which equation to use as a result of that. All right, let's look at that equation that we just learned in a little bit more detail here. E, of course, is the electric field. Okay, the electric field. We've done that before. It's the same electric field. It's just that this time it's in a uniform field. Delta V, we'll talk a little bit more in a couple of days about what that means. But for now, we'll just give you a brief definition and explanation. It stands for what we call the potential difference. Potential difference between the plates. So what does the potential difference between the plates mean? Well, it relates to the energy. It's not energy, but it's related to the energy, and that's good enough for us right now. It relates to the energy. So the energy kind of one plate as compared to the energy kind of the other plate. The potential difference is related to the energy between the plates. Units for potential difference are volts. And that's going to be a little bit confusing. The symbol is delta V. The unit is V. The potential difference between the plates is volts. The potential difference between one terminal of a battery and another terminal of a battery is 1.5 volts. Okay, when you look at a battery and you see that it's a 9-volt battery or 1.5 volt battery or whatever battery, that's potential difference. It's related to the energy between the plates. Delta D does not mean how far something's traveled, because listen, we're talking about the electric field between the plates that's caused by the plates. You don't even need anything to travel. You don't need anything between the plates to experience it. We still have this field. Delta D, rather, stands for the distance between the plates. And that's going to be measured in meters. So the electric field between these plates, the potential difference divided by the distance between the plates, measured in either newtons per coulomb, the unit that we've always used until this point for electric field, or a new set of units that means the same thing. Anybody tell me what that new unit might be? Look at the equation here. What's the new unit for electric field? Right, volts per meter, which means exactly the same thing. The two are interchangeable. Use whichever one works for you. One more quick little thing before we flip the page and compare some equations here. The electric field that surrounds this producer, this point source producer, this non-uniform field looks something like this, right, where the field lines are not parallel. That's how we know it's a non-uniform field, because the field lines are not parallel. They're closer together in one place than the other, so it's stronger in one place than the other. The electric field lines that acts between two parallel plates still goes away from positive toward negative, but these field lines are parallel to each other. And because they're parallel to each other, it indicates that the strength of the field is the same anywhere in between those plates. You find that field E is equal to delta V over delta D, that's going to be the strength of the field right here, here, everywhere. The strength of the field everywhere in between the plates is delta V over delta D, as opposed to, in this one, the strength of the field here is different than it is here, and it's different than it is right there. One last little thing, little chart on the next page here. You see three equations on this chart. The first two we've already seen quite a bit over the last few days. The last one is brand new today. Sometimes what I like to do with these three equations is draw a Venn diagram. You guys know what a Venn diagram is? What's a Venn diagram, Kenton? Yeah. two, or it could be more than two big circles, right? But right, shows what's similar, what's different between different things, right? Let's draw a Venn diagram around these equations. The first circle is going to go around the first two equations that we've already seen many times over the last few days. The second circle, we'll go with a fancy color for this one, purple. The second circle is going to go around the equation that we just learned today, in addition to the experiencer equation that we've learned before. Well, what's similar about these? What's different about these? The first two equations can be used in a non-uniform field. In other words, if we have the point source producer we're allowed to use this equation, and if there's an experiencer in there, we're allowed to use this equation, the experiencer equation. But we're allowed to use both of them in the same situation. It just depends upon what you have more information about. Now, the second two equations, the experiencer equation and the new equation that we just learned today, they're valid in a uniform field. In other words, we have an electric field that looks like this. Maybe there's an experiencer in between there somewhere. Whatever. They're both valid. It's just a matter of whatever you have more information about, the plates or the experiencer. So red, non-uniform field. This one right here, maybe you got an experiencer in there somewhere. Purple, uniform field, maybe you got an experiencer in there as well. What else do we know about these? Well, the electric field E is equal to KQ over R squared is the electric field around a producer. This is the experiencer equation. And of course, this one is the electric field that's between two parallel plates. Can you use the first one for an experiencer? No. The second one, yes. And the third one, really I should say no there. Yeah, I should say no. You can use it in conjunction with the experiencer equation. But it's for producers, right? The parallel plate producers. And then finally, can you use the first one between two charged parallel plates? Yeah, no, you can't. The last one, of course you can, because that's what it's for. And the second one, yeah, you can, if you have an experiencer between those two parallel plates. Honestly, the way that I determine what's valid and what's not, I think of the Venn diagram in my head. I picture that Venn diagram in my head. Okay, I picture what's in red, I picture what's in purple, and then I say, okay, what have I got? Do I have this one? Or do I have this one? And then I look at which equations are appropriate or which equations are valid based on that. All right, let's take a look at one quick example, 11.9 on 568. It says a cathode ray tube computer monitor. We don't even see cathode ray tube computer monitors anymore. They're all LCD screens now. Okay? What you see up in the corner there of the classroom, the old television set, that's a CRT television, a cathode ray tube television. You can't buy those anymore. Who wants to even buy them? They take up so much space, they weigh a ton, and they're more expensive than LCD TVs. So why would we even want them? Anyways, this is what we used to use all the time, is these CRT monitors. And the way they work is by accelerating electrons between two plates through a little hole in one of the plates, and then those electrons smack into the screen. The screen is painted with this coating, with a special kind of paint that glows when the electrons hit it. And that's the picture that you see on the TV, is the glowing screen as a result of the electrons striking that screen. We're not concerned about any of that stuff right now. All we care about right now is the plates. We're told that we have a distance between the plates of 1.2 times 10 to the negative 2 meters. That's going to be delta D, distance between the plates. not how far an electron goes. I don't care how far the electron goes. I care about how far apart the plates are. If the electrons happen to go the same distance, well, that's great, but it doesn't really matter to me. I care about how far apart the plates are, delta D. And I also care about the potential difference between the plates, not delta V, not delta little v, delta big V, potential difference. I want to find the electric field. So let's say E is equal to delta V over delta D. Pretty easy question, right? Delta V is 2.5 times 10 to the 4 volts. Right? That's a pretty big potential difference compared to what you see in a battery of 1.5 or 9 volts, right? Delta D is 1.2 times 10 to the negative 2 meters. We do the math there. 2.5 divided by 1.2 is going to give me 2.08. Just hold on one second, guys. 2.08 times 10 to the 6 volts per meter or newtons per coulomb. Now, real quick question here. I could have asked you the force experienced by the electron as it goes between those plates. We're not asked that in this question, but we could have asked you that. All you would do in that case is say, look, I know that both of these purple equations are valid in this situation of parallel plates. I use one of them. I use the new one that I learned. I can also use this one. E is equal to F over Q. I now know the electric field that's produced between the plates, or the electric field experienced by the electron that accelerates. I know the charge of the electron. I could find the force experienced by the electron as well. Does that make sense? Here's your homework. Practice problems on page 568. You're also going to have over the weekend, if you want to get a head start on this, go ahead. You're going to have worksheet number 8 as well. It's not due for tomorrow, though, just for Monday, okay? This is due for tomorrow. Worksheet number 8 is going to be due for Monday. Got it? All right, guys, that's it for today.